So now we'll move to the last event of the session of the workshop. It's a panel. Will be moderated by Professor Barney Maccabe. Here is a big bio, but I think
You know, for a really long time, everybody knows him.
Don't try to read that.
no, yeah. So I think many of you know him. He has been at multiple places, starting from Arizona State University to University of New Mexico.
Don't do that.
Okay, how about this? He's been around for a really, really long time. Everybody knows him.
Everybody knows him. Okay.
You're from Michigan, right? I mean, never mind.
No. So he will be having the, I mean, just one joke. Okay. So yesterday we were talking, and he's continuously hopping jobs to have more and more pensions. He's on a roll to get multiple pensions at any given time. Anyway, so today we have an exciting panel. It is
If you can't do one right, try several others.
Oh.
No, we can't hear you, Steve. I'm sorry. Would you try that? The connection's bad.
Okay, go, Steve.
No, ignore him. Really, ignore him. He'll be back.
So, let me give the floor to Bud.
Okay, thanks. Thanks, DK. It's actually, Steve, I was hoping I would actually see you here. I really was looking forward to that, but it's great to see people again. Thank you guys for organizing this. Thanks everybody for sticking around. I think we do have an exciting topic. So a little bit of background, and I'll get started. I've got a couple of slides we'll go through. I'm going to leave the slides, and I think that's the most important thing because I want to get us to the panel and get the panelists time to talk, because I presume that's really what you want to hear. Do we have one panelist remote? Is Debbie?
Who is
Debbie Bard is there? Can you check to see?
I think Debbie, I didn't see Debbie.
Yeah,
Okay.
Debbie is there.
Okay,
Yep,
good.
I'm here.
Excellent. We're ready to go. Okay, so this is the title. So let's go in here. You can leave it on the next slide.
Okay.
Can you please share the slides, Hari?
Yeah, hold on.
Oh,
Hold on.
I can see them here, so therefore everybody else can see them. That's all I know. So while we're going through this, I am now the executive director for the newly formed Institute for the Future of Data and Computation at the University of Arizona. For me personally, this is a return home. And so completing a great cycle going across various places in the United States. The nice thing about having an Institute for the Future of Data and Computation is, first, it's in the future. Second, it's about data and computation, and everything in the world is going to be about data and computation. So I really get to decide what I'm doing myself as we go along. And which button advances?
Right.
There we go. Yeah. And so this is the slide that is a bit from my sponsor. So this is what I'm doing roughly. I'm going to leave this. I'm not going to talk to this slide. I'm going to move on to the topic for the discussion today. And that's about distributed systems. So the history here is maybe about 5 or 6 years ago in the DOE national laboratories, in particular in the science laboratories, we started projecting what are we going to do after exascale? What's it going to look like? And it was obvious that data coming out of our instruments was going to be a big driver, right? And so we started to talk about how do we build distributed systems, and how do we start to think about them where they incorporate the science instruments like the light sources and the other major science instruments that we have at the laboratories. And this is one of my favorite definitions in Leslie Lamport, and it goes back in the history of how distributed systems were thought of and conceived of. This is like 1978 in that time frame. He was at Xerox PARC at the time, and they were just printing up a bunch of Altos, and he wanted to print things, or somebody else was doing something, and of course that's just the wonderful quote that he came up with is, somebody you didn't know about can make your machine not work. This is the definition that I was raised on from Philip Enslow, fully distributed systems. I'm not going to make you read this. The important notion here is that we were really trying to think about building a distributed system out of a bunch of junk that happened to be out there, right? And how do you make a coordinated computation run across all these different platforms, all these different various things that we're just pulling together? Remember 1978, the internet hadn't existed at that point. There were people doing ARPANET. There was a bit of people connecting things up, and that was just getting started. The real critical issue we're trying to address in this program was understanding how you cross multiple administrative domains. We came up with this notion of cooperative autonomy, right? So the idea was they would cooperate on a intention, but they would be autonomous in their execution. Now, that led me, when we started to think about this, connecting up the instruments, to think about, well, I'm going to put computation near these instruments, so I'm going to take whatever compute resources they have, and I'm going to try to figure out how to connect those and how to bring them into a large-scale computing platform, something like Frontier. And that's sort of the configuration we came up with. I entitled it Federated Instruments, the notion of federation as opposed to centralized or authoritarian coming down from the top. Jim Hack, who was running the National Center for Computational Sciences, had a different perception on how to address this problem. And his notion was, I'm building these massive machines. I don't even have floor space for them anymore. I need to start distributing that machine that I'm going to be building after an exascale platform. And what I want to do is put parts of that compute close to the instruments. And so I'm going to push my machine out. Like a completely different conceptualization of this kind of a problem. And it says you're going to push things up. Now, the interesting thing is the technologies that we're starting to hear now, slingshot and things like that, enable that campus area network to connect directly in as if it were part of the regular fabric. It may be a little difference in performance, but you're starting to see that potential. So there's technology breakthrough that makes that possible. And so pushing things to the edge becomes a reality. I'm still not convinced, and that's part of the reason I wanted to have this panel, is I'm not convinced that this is the right way to go forward. And I want to hear from a few of you others in terms about how that works and how we think about that and how we should consider that. The one thing I would point out is that when I started looking at parallel computing, I came at this with the conceptualization from the concurrent programming background, operating systems, and how you build up these large programs. It would have never occurred to me that single program, multiple data is the right way to go forward in parallel programming. So, and part of this is saying, well, maybe this simplification or this transformation of the problem into a more scalable or maybe more meaningful framework might be the right way to go. And so I'm willing to be open to discussion. Okay, and then the last thing about the extreme heterogeneity, I believe, at least right now, the way we're looking at extreme heterogeneity, it's may break the SPIN-D model. We'll see how that goes and maybe back to the more traditional form. Okay, with that, let me introduce the panel real quick. There's the charge questions I asked them to think about at least. If they don't answer those directly, that's just fine. We'll have a discussion. Here is the panel. Sadaf Alam from CSCS, Debbie Bard is at Berkeley, Robert Eicher from Munich, and Rich Graham from NVIDIA. And I still put no on some because I can't think of you not working at no. Anyhow, with that, I'll ask Sadaf to come up. We'll go in that order as sort of the plan is to have Sadaf go, and then Debbie Bard, and then Norbert, and then Rich. What do we need to do for slides? Oh,
I have no slides. I
Oh,
thought
just
no one would
that's
be here.
excellent.
Yeah, you can just talk.
I mean, it's the last session of the last
Oh,
day.
come
of the
on,
talk,
Sadaf.
so I was like, no one will be here.
Have more faith.
I didn't. So thanks for sticking by, and thanks for whoever is of their online. So now I will start from the pension plan model thing. I think we made a little mistake there because, you know, they say diversify, which you have done institutionally, but from a currency point of view, you should take my approach, go to different countries because you don't know how the currency situation will
Gain more ideas.
Yeah, so I think next time.
Was
Okay.
that a job offer?
No, I have like 3 currency moments so far. I keep trying. So sorry, I would like introduce myself. So I'm Chief Technology Officer at CSCS. Been there for Chief Technology Officer at the Swiss National Supercomputing Center. Been there for 13 years. Before that, okay. So I will share my perspective. So because I looked at it and I said, why is he making me think top down? But my experience, I should tell you where it comes from in making some hopefully informed comments about this instruments, federated instruments concept. So we work very closely. So at CSCS is Switzerland is small, so it's a single national supercomputing facility. We provide the research computing, general purpose research computing facility. This giant is the system you probably heard about, but we also provide what we consider mission-oriented systems and solutions. So MODULAR, which in most countries are separate entities, we run that service as well, operational weather forecast. And at the same time, we provide compute and storage for instruments such as, in the US could be like SLAC, SNS, and others, but in Switzerland, Paul-Scherrer Institute. So we provide them data storage and processing. So in my mind, this whole idea of federation is important in the sense, so now I put my head and say, when I look at weather and climate workflows, operational weather forecasting workflows, they come with completely different data processing and quality of service requirements. As they say, you do not want your weather forecast to be failed, otherwise no longer a forecast, which is different from an operational batch-oriented system type of model. When we work with PSI, the way the data is generated, they want compute very close to the instrument for all sorts of reasons. But at the same time, they are generating now so much additional data with the equipment. They want to be able to offload that data for online processing as well as offline processing. And so they are working with us in terms of how they can build version of their systems together with us in this federated mode. So one idea would be to maybe consolidate the system, but you cannot operate multiple quality of service and data acquisition and simulation domains in one system. So for me, I think it's looking at it from the point of view top down and bottom up distributed systems is a wrong way in my mind to think about it. So I'm giving a new idea. I'm bringing up a new idea here, and which is not more than an idea, by the way. We are really working with them closely on these things. What we are saying is, why not we look at it that you create really infrastructure in a programmable manner. And what does that mean is that essentially PSI, in this case, or MODULAR in other cases, they can create a specialized instance of their infrastructure close to the source, where they have lower latency, high processing, high throughput requirement, but they can generate an instance of that infrastructure closer to where there is massive compute and storage facility, namely CSCS. And the important thing why they want to do it, because they have their own customers and providers. And one thing you say, which I cannot agree more, is that we are really not talking about different technology domains. We are really talking about not only different administrative domains, but different business domains, because the IT that is funded in MODULAR operates in a different funding cycle of usage cycle, another thing, etc. Or the funding for IT, I'm simplifying IT in a generic way, but this large scale IT included at Paul-Scherrer Institute has a different model. And that brings this whole identity and access management part, which I'm a little bit embarrassed to say, in supercomputing, we are working on 1970s or 80s identity and access management model. So to me, we should really look at it not from a system point of view, but from an identity and access management point of view based on these business requirements, and then design, I should say, these lateral systems, not top down, bottom up, but based on some of these use cases. And that is the way that these are the things we are working on. Like when we are building out, we are really trying to look at it, how someone can program part of our supercomputing infrastructure. So these are kind of the thoughts I don't want to go and bore everyone after 5 p.m. here with the weather and climate thing. So how about this thing? Not top down, not bottom up, but in a bit more way, flexible and lateral approach, where sometimes the emphasis can be on bottom side, because that is how the funding, the resourcing, the business model can be optimized, and sometimes it could be, top down, because that's where the resources. The Swiss government is not going to probably give a lot of funding to PSI, because if they say they have invested in a lot of GPUs like CSCS, that is the place to go and exploit it. But at the same time, they can't put like billion-dollar instruments and say, no, you cannot do low latency processing closer to the equipment. But we need to really enable the administrator of the IT infrastructure to work across these organizational and business boundaries in the seamless way, where I think the thing, at least I'm focusing on at CSCS, is this identity and access management for federation, which is pretty much what cloud do, but they do it in a different way from the cloud speed. But I don't want to talk about it. So here is a different perspective. Sorry, I didn't answer your question. So it means I've given you more homework.
So I think I heard you say that it was going to be bottom up for the most part, or federated, with the potential of pushing some equipment out. And part of this is how do you administer these systems, right? Is there a centralized authority that's administering them? Are they completely separate? That's kind of that issue, right? And that federation is sort of the bottom up. Debbie, you're up next. Thank you so much for getting up early in your morning. It still is pretty early out there, if I'm not mistaken. I try not to think about what time zone, and it's much easier that way, but I'm sure she's well aware. So Debbie, it's all yours.
Yeah. Thank you. Yep, right. I'm bushy-tailed. It's only 8:20 in the morning, so it's not too bad. I do have slides that I'm going to share. Although,
You should be.
Stop sharing on this side.
Yeah. Go ahead.
Thank you. All right, and a lot of the points I'm going to make actually are very similar to the ones Siddharth just made. We have a similar, I think, set of issues that we're dealing with our user base. So I'm going to talk from the perspective of NERSC, where I work, the National Energy Research Scientific Computing Center, and sort of thinking about the challenges that we face at NERSC due to our role as the mission HPC and data center for the Department of Energy Office of Science. What this means is that we have something like 8,000 users running on our systems. I just had a look right now. We have 1,200 jobs running on our Cori system, which is a lot to handle. It's a lot for the network to have to deal with. And I want to focus on the unique needs of the experiment and observational science community, because that's the science community that my team works with specifically. And so this is very much in within the concept of the Superfacility Model. So at Berkeley Lab, our idea of the Superfacility Model is an ecosystem of connected independent facilities. So this would be, for example, an experiment facility connected to ESNet, connected to NERSC, or one of the other DOE supercomputing facilities. That allows the scientists at one of these experiment facilities to easily use HPC for their data analysis and modeling. But I think that the overriding point I'm going to be making in the next few minutes is that just connecting the hardware together is not sufficient to make this model work for scientists. The software ecosystem, the amount of expertise required, and the policy issues above all are the really tricky parts to making this kind of model work. This is where I'm coming from when I'm thinking about a distributed computing ecosystem. So I do think of this as the bottom-up approach, similar to what you all were just talking about. This is already happening organically. We already have many science teams that are juggling their own on-site computing. They're juggling allocations at HPC centers. They're trying to coordinate data and compute tasks across the sites. And what we're trying to do at NERSC via the Superfacility work is to put in place the policies and technologies that can support this work and enable this work. And Federated ID is one of these. Programmable API interfaces to as much functionality as possible is another important one, because this is already happening from a bottom-up perspective. And so what we need to do is make this model easier to use for the scientists, to remove a lot of the barriers that are in place for this. And honestly, I think when we're looking at this from the perspective of the DOE complex, a lot of these challenges have to be done top-down. It can be very difficult from a bottom-up way to try to solve the problem of federated ID across multiple independent DOE facilities that each have perhaps different security stances, different requirements, like different levels of nervousness about sort of exposing perhaps functionality via an API or having federated identity. This is something that has to be done from a top-down. And when I say top-down, you know, I mean from the federal level. This has to be something that is organized at a high level rather than just kind of trying to let it bubble up organically. So I'll give an example of this, similar to the PSI example that Siddharth was talking about. This is the XFL project, which is building an exascale capable workflow to analyze data from the LINAC coherent light source, which is X-ray free electron laser at SLAC National Accelerator Lab. And they have to burst their compute to NERSC when they run an experiment that has a particularly high data rate, because they need to have real-time analysis of the data to give feedback to the beamline staff. And if they have a small data volume or a low data rate experiment, they can handle that with their local computing. But when they have a high data rate, they need to burst to HPC to do that analysis. And with the upgrades coming to their detectors, they're expecting to be of an exascale class burst. You know, we're talking a very large amount of computing that's required at very short notice to analyze the data. So it's kind of an exciting challenge, both from an application point of view and from this idea of the distributed ecosystem. How do you design a workflow that can function at local compute resources and can burst out to HPC at very large scale? So this is something that is already running at NERSC, not at the large volumes we're expecting in the future, but this is the kind of use case that we see as in increasing use case. There are more and more experiments that are trying to operate in this mode. It's something that's really challenging, and it's a new challenge for HPC centers. And this is kind of where the economic considerations come in from my perspective. DOE invests many hundreds of millions of dollars in the research infrastructure in these user facilities. And really, to make efficient use of this investment, we need an integrated research infrastructure for computing. And that is, you know, what I was just talking about. Experiment facilities need to be able to use the appropriate computing resources when they need it in order to maximize the investment in time and money that has been made in these big facilities. And I think it's also fair to say that we are still in an era where computing is not always thought of in the first instance when a funding agency or a facility is putting together a new experiment. We still see many large investments made in science facilities without an equivalent and necessary investment in computing resources. And so this is another economic consideration where science teams, just as Siddharth was saying, are often told, well, you've got this big HPC center that you just buy or just connected by ESNet, another DOE facility. Use that instead of us investing in local computing. And that's a real economic driver for this as well. I also want to make the point that hardware and equipment costs are not the difficult part here. The difficult part are kind of the people costs. And This is particularly true for smaller science teams. They don't necessarily have the personnel or the funding or the time or the expertise to develop their workflows, to port to a new system, a new architecture, to take advantage of all the kind of technologies we've been hearing about in this workshop. It's hard to hire for skills in this area. We certainly have that problem at HPC centres, let alone in the experiment side. And so this is one of the challenges that we have to think about when we're thinking about deploying new technology for this kind of use case. Because there is this natural tension between, we want the most performant technology, we want the new features, we want to be able to deliver better performance for our users, but our user base is not necessarily able to take advantage of it. And so that puts some burden on us at HPC centres to be able to kind of abstract or hide that capability away from the user, so they don't have to redevelop their applications and workflows, every 5 years. Because many of the projects we work with are multi-year, and so they just don't have the capability to optimize so frequently. So having sustainable and reliable interfaces like API interfaces can really smooth this transition. And another point that I think I want to make is, as HPC experts, we love to optimize the heck out of our applications. We want things to run as efficiently as possible and be able to go as fast as they possibly can. But most scientists we work with strongly prefer a predictable and reliable performance from their infrastructure. They're willing to take a hit on the speed and performance. Is not a huge hit, they would like to have both, but in general, people would like to have something that is predictable and reliable. It can be very frustrating for someone running a code on an HPC at an HPC center if one day it completes in 2 hours and the next day it completes in 8 hours. Like, that's a difficult thing for them to have to manage, like just in terms of how they handle their compute allocation and plan their work. So this is a big theme for us. And this is where developments in interconnect technologies are interesting. The ability to handle QoS in the network is important for that. But I also want to point out that the bottleneck for cross-facility workflows or removing data between sites is actually data ingest at the facility edge rather than data within the borders of the system or within the borders of somewhere like NERSC. This figure shows the bandwidth of ESNet, the Energy Sciences Network, the bandwidth available at the NERSC border, at the NERSC backbone, to bring data into Perlmutter and then within Perlmutter system itself. And so it's a huge contrast. And so this sort of, when we're trying to bring in lots of data from a streaming experiment at the edge, the bottleneck really isn't our edge network. It's bringing the data in through the wide area network. And so this is a different set of problems, and how we handle that, the QoS for that kind of challenge. But to talk about wireless technologies, as I was specifically mentioned, an emerging use case which I'm pretty excited about is HPC being linked into distributed sensor networks, which is really enabled by wireless technologies. So you might have a distributed sensor network that's monitoring a watershed or a wildfire, for example. Progress and the conditions on the ground that is enabled by wireless technology, and being able to plug that into HPC is something that's really new for us. But we see this in the next 5 years as being a much larger use case for us. And so we don't yet know what the challenges are going to be with this in terms of networking, but it's going to be interesting. All right, so the last thing that I'll say is that software infrastructure is going to be critical for shaping this future and the challenges that we see for us in the next 5 to 7 years. I already mentioned software capabilities like network QoS, but I'll emphasize again that it's building the hardware is not the challenge here. It's the software, the interoperability, the sociological challenges, and the policy issues that I see as being much more challenging. And there are things that we can do from the software perspective to help make those challenges easier to address. All right,
Okay, thanks.
That was
The example of Slack is actually a really interesting one because that is a fact where you don't get to control. So you wouldn't be pushing part of NERSC over to Slack. That's just not going to happen, right? And so you have to deal with that multiple administrative domain. Yes,
Can I ask a question?
sure.
Yeah.
You guys are going to talk later. Don't worry.
No, no, no.
We'll get you up here.
Should be a short one, but it's a curiosity and we can take that later. So you made a comment that the federated ID should be top-down approach. In Europe and other areas, and I think part of it somewhat US entities are involved. We are taking it as more sort of a distributed based on trust or level of assurance. So I'm just curious, is there a specific reason you think it should be solved in a centralized way, or it can't be done through other, attributes and features that are available in modern identity? I mean, there needs to be some kind of agreement in terms of level of assurance and trust, but I was just curious. Because if we put it, for me, if we put it like that, we won't solve it.
Yeah, the way I see it is if it's not done top down, it won't happen. A lot of user facilities are very nervous about buying into federated ID because they can be very security conscious, and so we need to have strong endorsement and direction from the federal level to kind of give us permission to do federated ID. Now, we've already put in place federated ID at NERSC with other DOE labs that have the same security stance as us, and that's has been fairly straightforward in terms of technology, but it's been really, really hard in terms of getting the policy right and getting agreements and endorsements and buy-in from our funding agencies. So I think this is something that the funding agency has to be strongly in favor of to make it work. So from that perspective, that's kind of why it has to be top down.
Okay, thanks again, Debbie. Robert, you're up.
Okay, thank you. Yeah, so my name is Norbert Alka. I'm from the Supercomputing Center. Okay, and so I work there since 18 years, something like that. So my main task there is to look into future technologies, future computer architectures, so future cluster architectures, basically. And so the last decade, I happened to work on these sort of projects. So started with deep, then deeper, deepest, and now we are in the deep sea. So the key idea that we worked on there is, so we started with looking at how to organize heterogeneity in the supercomputers, right? So 10 years ago, it became obvious that accelerators will play a dominant role in future supercomputers, and so the standard way to integrate accelerators, of course, at that time was so plug one GPU or some other accelerator into each node and then scale this out. And of course, this has some problems. So there are always applications which cannot really benefit from the accelerators. So which means that we invest money into hardware which you then cannot use. Then there are other applications which can pretty well benefit from accelerators, which then suffer from the fact that you just put one or two accelerator in each node and they could use more of them. And so we over the time developed the idea what we now call the modular supercomputing architecture. And the key idea is to not have heterogeneous nodes, so but all nodes identical with different hardware components in it, and then scale this complex node out, but to organize it in a different way, to go with what we call modules. the idea is a different shape. I think in almost every supercomputer, you typically have partitions, right? So so typically you have some nodes which say have larger memory, stuff like that. And yeah, we try to push this idea of partitions or modules, as we call it, a bit further, so that you can use resources out of different modules at the same time, right? So, and if you have an application that can benefit from an accelerator, but has a different part of the application which which cannot benefit from accelerators, then you would put the part that cannot benefit from accelerators on what we call the cluster. So it's then a cluster purely CPUs, and then put the part that can benefit from an accelerator on a different module, what we call the booster, which is just a cluster with accelerator, right? And then you can pick resources specifically from both sides and pick them with a ratio that suits your application the best. Well, once you started to, and this is what we did in a first project, basically, so to create the cluster and booster. The booster at that time was Xeon Phi, just with the idea that you can even drop the CPU in this part, since you have accelerators which can act autonomously. So once you start this idea, of course, you can extend it. So you can think about having applications that say need way more memory and maybe some local storage, and then you define a module which we call the DAM, the data analytics module, in order to put parts of your application there. And of course, you can think about say non-von Neumann type of compute devices, right? Like neuromorphic modules, or for example, quantum modules. And actually, in Unity, we are currently having a project besides DeepC. So we already have a quantum module, so which happens to come from E-Wave, and we are on the way to get a different module, which is which follows the gate quantum computer model. And and we are convinced that that in order to use such a quantum computer, you typically need a pre and post processing, and this pre and post processing typically is quite heavy. And so for this reason, we think that it really makes sense to couple a quantum module to classical HPC resource. And as I said, so we have one project where we look into how to couple these. And so now let me come back to your original question. So is this top down or bottom up? And actually, I cannot really decide. So of course, well, you need so like user management, this has to be top down, obviously. On the other hand, so the quantum module typically has to be in a different hall, because it has totally different requirements on the environment, right? So it's you have to shield all type of magnetic fields. So there shall be so you have to ensure that nothing is moved in the house. You have to provide all the cooling infrastructure, and this is typically not compatible with the other HPC systems that you have. So which means, well, you set up a different building just for this quantum module. So from this sense, it's the other way around, right? To answer your question, I cannot answer it. So it seems to be a kind of combination of both, and I'm not sure if this so how much sense this question actually makes. Sorry. Okay.
Rich, you're next. And one thing before, as Rich gets here, my old cynical statement on this, and this was before I went to the national labs, and luckily, Oak Ridge National Laboratory didn't have an HEP program. But my statement used to be that HEP, the high energy physics community, reinvented distributed computing and did a really bad job of it. Now, part of this goes to is we just leave the physicists to go build their computing infrastructure along with their instrument. That's part of my big concern going into this, right? And part of this notion that if we just leave them to build whatever they want to build, we're going to have to deal with a bunch of stuff. Right? And rather than that, hopefully we get more computer scientists, or if you get more of a push from the central authority, people who know how to build computing infrastructure. Rich is taking his time, so I get to keep talking for a while. But if you take people from a central computing capability that know how to build computing infrastructure, know how to connect it in, there's tremendous advantages to that. Right? There's also big challenges. Oh, now Sadat is back up again. She said, tell me where I'm going.
Yeah. Because, I agree partly, but not fully. Yeah. They know that supercomputing facility, when you say I'm going sort of bashing on my own community, they have learned to build infrastructure, but they have learned to build in a very static and rigid way, and they are not moving away from it. And this is like the part of the problem also. Yes, so it would work if they would listen what physicists think, and vice versa is also true. So, I mean, we can go on these things about grid computing and whatnot for distributed computing as a solution. But if I look at that, even in the grid computing world, they are adopting some of the software technologies being developed in cloud computing. If I look at it, the distribution, software packaging, and distribution model, the closest thing that has come right now, which is far away from where we need to be, is stack package manager from ECB. We move like a big thing. So yes, this is good, but as a computer scientist, honestly, are we building the systems the right way than really that? No.
And now we got Norbert up, so you're going to take a while, Rich.
That's
Yeah.
Yeah, so I have a different example. So we really are also involved in this human brain project, right? And this also poses some challenges because, well, the people from the neuroscience, so they have nice ideas. So like, well, it would be really interesting to do interactive supercomputing. And obviously, this is fully incompatible with how we run the system.
Okay, no, you're going to come back. I'm going to let Rich talk. Boy, you just stepped on one there. Here.
This is how bad it's supposed to be.
So my name is Rich Graham. Can you hear me? Okay. My name is Rich Graham, and I'm from NVIDIA/Mellanox. I'll follow Barney. That's right. So I've been there for about 10 years, focusing on areas of HPC and the like. Before that, I actually reported to Barney. And before that, at Los Alamos. But anyhow, so I can tell from being in industry now for 10 years, I certainly have a different perspective on things. So I took a very different tack at answering. So these are more of my notes to myself than anything else, not intended to say much. So when I started to think about this question, bottom up or top down, I thought from a hardware technology perspective, do you have the freedom to just invent anything you want to throw at a customer to use, or do you need to live within constraints of something that can actually operate? So and focusing less on how you would string the pieces together, because different customers string things together in different ways, right? Same hardware, different ways. Even when it comes to the network, you have a whole bunch of different topologies that you can use to build a network, for example. And so I think from when I think about it in those terms, can I, do I take pieces off the shelf and go from bottom up? Well, in the short term, when you have to deliver something that works, what else would you do? I mean, that's sort of unless you want to sell a bunch of FPGAs and let people configure their own FPGAs and their own system and the like. I suppose you could do that. But on the other hand, I remember 20 years ago at Los Alamos, when people started to look at this gaming type of programming. I can think of 2 projects that happened at the time there. Steve mentioned one of them. There was the Viz folks at the time, Pat McCormick and Jim Ahrens and the like, that started playing around with these things that were very, very difficult to build. And now 20 years later, these are the systems that are being sold. And so there's certainly room for both of those. When it comes to edge computing, so from my perspective, there's a lot of the pieces of technology that exist today that can be used. I'm sure that looking forward, think about how to do it better. And of course, software. Well, I guess we get to software later. So from my perspective, I think both of them are essential, right? If we want to move forward long term, we have to be thinking about these things that won't work today. So that's briefly about that on that question. Again, coming from a perspective of needing to make something work, the economy always impacts things, right? If you don't have money and you can't sustain it, then it's not going to be able to build it. And so, but on the other hand, if you don't have these risky projects that are really research funded, that may fail or the like, then we never move forward. So there's certainly, both of them are essential to move forward beyond where we are today. Let's see. Again, technology refresh. I wasn't sure exactly what you were coming at there, so I was trying to guess.
When you build a light source, it's for 30 years.
That's right.
When you build an HPC system, it's for 3 years.
Yeah, 2 or 3, exactly.
That was what I was trying to get at.
Yeah, so I guess when you look at it that way, people do try to build systems that that they can expand and the like, but it gets it's a lot more complex, at least in computing. If you have to work on have to use a real heterogeneous system, not just maybe some well-defined pieces, but pieces with different rates, can get good efficiencies out of them. So from that perspective, I guess you could do some planning for it. Again, this is from the short term, not the long term, not the 30-year term, but more the 3-year term. So I'm not really quite sure what to say. Nothing very obvious. So do I need to say more? No, so I didn't, so that's sort of the obvious. I mean, because distributed systems, something has to interconnect it, right? So, but being a little more practical there, wireless. So I didn't think of these remote sensors, which are of course important. I thought about some of the things that we've built around periodically. Having a very big microwave in some room or something like that. So again, not being a hardware guy, I'm not aware of all the issues there. And so at least from the perspective, yeah, I don't know. And from the software question, somehow I jumped over that. So I'll say at NVIDIA, what I'm learning is, even though we're a hardware company, about 3/4 of the people are software. And the software, that's what runs. And so that's great.
Okay. We have a little bit more time, and I want to, I'll pass my seat. Don't worry, we'll get back to you. I did want to get to Debbie. She's been quiet for a moment, and I want to point out, I think that the one thing she said, I think that is absolutely essential here is you have to define the interfaces. Like, and those have to remain relatively stable over time. And then you can free up. And part of the question here is, how far does that interface push out? How far does it go all the way to the edge right next to the instrument? Right now, a lot of the computing is embedded in the instrument, right? Part of the thing here is I would expect we want to get the computing out of the instrument, so at least there's a freeing up the timelines of the refresh rate, right? Because computing is going to continue to evolve very, very quickly. And how we think about this, and so you want to separate those out, but you have to define the interface. And I know, as I mentioned earlier, that NERSC has actually been very, that project with Slack, right? The people at Slack sing the praises because they said, we know how to interface to that system. And they complained about Oak Ridge saying, we don't have a clue how to interface to the Oak Ridge system. And part is because Oak Ridge, and I think the leadership computing facilities want to go back to what Norbert was talking about, and that is that batch scheduling is the best way to get utilization out of that computing system. If that's what your goal is, to get utilization, and that's your metric, then you're still going to have to fight that. And we've tried to fight it, or Oak Ridge has tried to fight it for a while. But I'll let Debbie have a word for a moment.
Yeah, we've actually just gone through a process of redefining our metrics, our success metrics, you know, the reportable metrics that we give to our sponsors to include what we call urgent computing. So this kind of on-demand compute load, so that we're, yeah, it's been a huge problem, as you say, sort of squaring the metrics that we report and the way we define success, squaring that with the changing needs from the user community. So that's important. The other sort of element is that, yes, scheduling of these kinds of workloads is really hard. It's if you don't want to have nodes sitting idle, sort of not doing anything, waiting for some compute workload that needs a short turnaround. You know, it's very difficult to schedule that. So we're it has knock-on implications to things like checkpointable workloads, and you know, technologies and how you containerize and perhaps be able to suspend workload to meet sort of a very rapidly changing demand. And this comes back again to being able to prioritize, for example, quality of service of different network streams that are passing through the center. Like it's a knotty problem that we're only just we've got something that works, but it's not yet smooth, and it's certainly, even at NERSC, you know, we've still got some work to do to make it something that will be able to work at other sites as well.
Okay, Norbert, well, I cut you off earlier, so now you can go.
Actually, I have a question to you. So you say the technology renewal cycles are different in HPC and in this big research facility. So how true is this actually? Because so if I think about LHC, so they shut down their system every 4 or 5 years in order to rebuild or to upgrade their detectors, and then they adapt that detector on the newest compute technology, because they then might get better data, more data. They have new measures in order to select the data that they actually take out of the system. And I would assume for this light source it will be similar.
No, that's
Yeah,
that's a great point. Go ahead, Debbie. Yeah.
So I think there's maybe 2 points I'd make here. One is that the software stack for somewhere like, you know, an LHC experiment has been developed by perhaps 10,000 grad students over 6, 7, 10, 15 years. It's very hard to shift something that's so big and complex to a new architecture. Parts of it have been successfully ported to GPUs, for example, but by no means all of it. That's one challenge. Another challenge is kind of the opposite side, where a long-term project, for example, some of the astronomy projects that we work with at NERSC, they have a very small computing budget, and they want to have consistent results all the way through. They want to be able to reprocess year 1 data and have it be done in the same way as the, you know, year 10 data. And they don't have the resources to be able to retool and optimize their code. So for them, an ideal system would be one that just doesn't change over the whole 10 years. They don't have to worry about losing data or inconsistent results over time. And so that's another challenge.
Yeah, I think that's right. I think that the LHC is unique or different in the sense that the sensors are continually changing, they're upgrading them, but what they've done is they separated large part of the instrument from the information processing, right? The sensor information at, you can find the interface at that point where you can move it in and out. I think the other point is, so when we look at the spallation neutron source, right, they set that up for a 30-year run. We go in there and look at the software, they had FPGAs connected to Windows XT boxes, that's how they get their data collection. Right? And as they're getting more data and as they're starting, the right sources are probably going to start to get that separation. Part of this is how to think about where they should be. But technology refresh is not just on what's available. As Debbie points out correctly, most scientists don't want to be on our exponential growth in or exponential change in the technology base. They want something that's going to work through the lifetime of their experiment, and that's good enough for them, right? And so that's part of that. Other places may want the continual upgrades. So now, Rick, you got kids like, oh, you don't want
Oh.
You're tired, it's after 5 o'clock?
No,
She's sad.
no, I said you don't want me to talk. But this is a good discussion, Debbie, and you started, and that's what I was trying to bring up, that we will have different approaches. Because if we now look at weather and climate, the one we work with, they work on a 4-year model-based thing, and why it is and how it is, I don't know, and don't care, but it is very important because they have their own customers in different other industries that use their products, and they have to work it like that. But media climate, domain working in that thing, they may work on a 5 to 10 year model. So yet these are really domain dependent and concepts. But what I was really initially bringing up was that for the most part, and especially if we set some scale target for a building a supercomputer, we start with so many constraints, and then we judge or pat ourselves on the back and we did it, it was whatever number of lists and things we got, and as a result, we know how to build systems for everyone. And I was really challenging that part. But you sort of answered it, the business domain that you are given to work with, that is to maximize the utilization of the system, forces you to build, operate, schedule things in a certain way. That doesn't mean that the neuroscientists are wrong about building their own system. That's what I was really trying to say. So we are operating with this in a certain constraint that take us to design the system, and what we are doing at CS is how we can make the design process more programmable.
Okay. I guess, and unless I'm going to have a couple closing remarks, we're about done here. I think the time. One thing I would point out is that if you have a centralized design and you push it out, you're much more efficient in how you drive that computing infrastructure, right? Because you know everyone's going to be talking the same language, they're all going to be in the same software infrastructure. You can find all of that as long as you can make it work. I think Rich's point of you got to build things, and one thing I would say, you don't want to have this centralized, there's a central solution, right? And it works in a lot of places. It does cut off all the experimentation. Think about MPI. MPI did really, really good things for the world, right? In terms of this is the standard, this is what we're doing, but it killed every other program on top. It crushed, right? And just about everyone, and people keep trying them, and they keep running into this problem of
No.
Oh,
Yeah,
we are doing but I think that those are important points to keep in mind, that it will push out a lot of the innovation and a lot of the experimentation at the edge, the new novel solution that you've got to come up with. So you have to find ways of doing that. You have to separate them out from what drives the core infrastructure. And what drives the core infrastructure will always be efficiency in some form. Right? And I think Debbie's point about how do you, what are the metrics you really care about? You've got to be careful about those, because if utilization is the only metric, then you're gonna go to batch processing. It says the machine is the most valuable thing in the game, right? Rather than the people, or rather than the experiments, or rather than everything else. And start connecting up something that's as expensive as a light source with a supercomputer, it's no longer clear where the resources, where the optimization really should be. Okay, I'll shut up then.
So
Yeah, go ahead.